Hello everyone and welcome to the next video in the series. This is a technical skills video on the topic of addition and subtraction of numbers that are written in scientific notation. And what I'll do in this video is I will illustrate the ideas through examples. So let's go right into them. Example number 1. Let's say we want to add 5.31 times 10 to the power of 2 plus 3.2 times 10 to the power of 2. Now, in order to explain how we go about doing this, I'm going to display an image on the right side. So here we have 5.31 times 10 to the power of 2, and we wish to add 3.2 times 10 to the power of 2 to the number above. You notice that I've lined up the decimal point, and the question is, will that work? Given that we have times 10 to the power of 2, keep in mind that when you multiply by 10 with an exponent of 10 that's an integer, it indicates that the decimal point moves forward or backward in order for you to go to the decimal notation. And of course, if I convert these two numbers to their decimal form, the top one with the top one decimal point moves forward over 2 digits, and we end up with 531. So you notice that 5 is actually not in the ones as it would appear here, but its actual true value is hundreds, owing to the fact that we multiply by 10 to the power of 2. In fact, if I was going to multiply this by 10 to the power of 1, then 5 would be worth 10, like it would be worth 50. It would be in the tens place. If you multiply by 10 to the power of 2, then 5 will be in the hundreds. If you multiply by 10 to the power of 3, then 5 is in the thousands. So here we notice that 5 is in the hundreds, and same thing for 3, because 3.2 is also being multiplied by 10 to the power of 2. Decimal point moves forward over 2 digits, and we end up with 320, and therefore 3 is also in the hundreds. And it's owing to the fact that we are multiplying by the same power of 10 that ensures that these digits have the same place value. So if they are both being multiplied by 10 to the power of 2, then 5 and 3 are both of them in the hundreds, as you can see here in the decimal format. If you multiply both of them by 10 to the power of 3, then 5 and 3 will be in the thousands location. So both of them will have the same place value. So the case where we multiply by the same power of 10 is pretty simple to work out. We line up the decimal point and add the digits. I will add the two numbers in the two formats, decimal notation and also scientific notation at the same time, so you can compare how the two of them progress. So in the decimal notation, we would add 0 and 1, and we would get 1. And here the 0 is of course here, and if we add 0 to 1, we'll end up with a 1 as well. And then we move on to the tens column in the decimal notation and add 2 and 3 to get 5. And we do the same with scientific notation, add 2 and 3 to get 5. Now we add 3 and 5 in decimal notation to get 8. And with scientific notation, now we put the decimal point, and then we add 3 and 5 to get 8 as well. Now we can of course add times 10 to the power of 2 at the end of it, which indicates that the sum as well, in the sum you have to move the decimal point forward over 2 digits to end up with the format in decimal, to end up with the decimal format. So everything works fine then, and therefore if you have the same exponents of 10, all you have to do is line up the decimal point and add up your digits. The exponent of 10 of course does not change. Alright, so this comes to 8.51 times 10 to the power of 2. Problem number 2. Now this time we are adding and subtracting 3 numbers, and the first one, the leading one, is negative. Negative 9.21 times 10 to the power of negative 3 plus 5.2 times 10 to the power of negative 3 minus 8.5 times 10 to the power of negative 3. So as before, we can perform, because all the exponents of 10 are the same. And in fact, it's also good to know that on the negative side, if you have negative exponents of 10, negative 1 implies that the digit 9 here, for example, if you have an exponent of negative 1, then this 9 is in the tenths. So its value in the decimal notation would be in the place value tenths. If you have negative 2, then 9 is in the hundredths, and if you have negative 3, the actual value of 9, or the actual place of 9, is in the thousands. So all of these have the same exponents of 10. 9, 5, and 8 are all in the thousands, and therefore we can again line up the decimal point and do our additions and subtractions. So basically what we do is negative 9.21 plus 5.2 minus 8.5, write that down, and then add on times 10 to the power of negative 3. And if you work out negative 9.21 plus 5.2 minus 8.5, you'll end up with negative 12.51. And then we add on times 10 to the power of negative 3 to the end of that. Okay, problem number 3 now. Now we have exponents of 10 that are different. And this poses a problem, because that means we cannot line up the decimal points. Because the digits, the place values will not line up. So again, if you think of times 10 to the power of 3 as implying that decimal point moves forward over 3 digits, that means that 5 is in the thousands. In 2.1 times 10 to the power of 2, the exponent of 2 implies that the decimal point moves forward over 2 digits, and therefore the 2 here is in the hundreds. And so we cannot really add thousands and hundreds. And so here's the image for this addition. So this will not work. We may not line up the decimal point. Again, if you think about the decimal representation, 5.48 times 10 to the power of 3, decimal point moves forward over 3 digits, and we get 5,480. And in 2.1 times 10 to the power of 2, decimal point moves forward over 2 digits, and we end up with 210. And therefore, as you can see, the 2 and the 5 do not line up. Now this has to do again with the fact that the exponent of 10 are different. So when you add numbers in scientific notation that have different exponents of 10, you need to make them the same first. Then you can line up the decimal point and do your additions and subtractions. Now in terms of what we should pick as the common exponent, you have options. You can go with the smallest value that you have, such as 2 here, or you can go with the largest value, such as 3, or even some exponent that's not here. You can even choose times 10 to the power of negative 1 as the common exponent. Now, for reasons that I will tell you about in a couple of minutes, it's always best to choose the largest exponent of 10 that you see. So in this case, let's say that we choose to convert both exponents to 3. So we have times 10 to the power of 3 for both of these numbers. Of course, the first number does not change. Let me repeat the decimal sum over here. And then the first number does not change, of course. So 5.48 times 10 to the power of 3. Now here, we would like to change the exponent of 10 to 3. So we want to have times 10 to the power of 3 in place of times 10 to the power of 2. And remember from one of the previous videos that if you raise the exponent, you need to move the decimal point back over 1 digit to compensate for the increase in size that you have introduced. And therefore we end up with 0.21 times 10 to the power of 3. Now the digits are lined up properly. As you can see in the decimal notation, 8 and 1 are lined up, same thing with scientific notation. 4 and 2 are lined up, same thing with scientific notation. Okay, so once again what we did, let me go back a couple of images, is we choose the largest exponent of 10 as the common exponent, and therefore we write the first number as it is, and as for the second number we want times 10 to the power of 3. That means the exponent goes up, and therefore decimal point moves back. Now, one advantage of going with the largest exponent of 10 is that because the others are smaller than that, they will have to go up. All of them will have to go up, and therefore decimal points will always move back. And this is helpful because you don't have to constantly worry about, decimal point went up, which way do I go? Back or forward? And now decimal point the exponent went down. What do I do now? Which way does the decimal point go? If you always go with the largest exponent of 10, all of the other exponents will have to go up to match its size, and that means that all of the decimal points move back. So exponent goes up by 1, decimal point moves back over 1, and we end up with 0.21 times 10 to the power of 3. Now we can line up, now that we have properly lined up our digits, we can start the addition. On the decimal notation side, the zeros add up, of course, to give us a 0, and these zeros are after the column 8, 1 over here that we don't have to write down. And then following that, we add 8 and 1 to get 9, and same thing here. Then we add 4 and 2 both in the decimal notation and scientific notation to get 6. And then we put down the 5 with the decimal notation, of course. With scientific notation, of course, you need to put down the decimal point as well. So we get 5.69. And then we add on times 10 to the power of 3. And you can see that we arrive at the same result. Here, decimal point moves forward over 3 digits, and we end up with 5,690. Alright, so if I was going to write it down here, I would repeat 5.48 times 10 to the power of 3. Now, knowing that this exponent goes up and decimal point moves back over 1 digit, we end up with plus 0.21 times 10 to the power of 3. Now we add 5.48 and 0.21 to get 5.69. And then we add on times 10 to the power of 3. Okay, problem number 4. Now here the difference between the exponents is larger. One is times 10 to the power of 5, and the other one is times 10 to the power of 2. So if I go with the largest exponent, then the first number stays the same. And as far as the second number goes, 2 will have to go up by 3 to match 5. And therefore decimal point moves back over 3 digits. And we end up with 0.0038 times 10 to the power of 5. Now we can add 2.98 and 0.0038 and add on times 10 to the power of 5 to the end of that. Now let's say we go with the alternative approach. Let's say that we, one alternative approach, let's say we go with the lowest exponent. We'll choose 2 as the common exponent. In this case, because 5 has to come down to meet the value of 2, what we have to do is move the decimal point forward over 3 digits. And therefore we end up with 2,980 times 10 to the power of 2. And 3.8 times 10 to the power of 2, of course, doesn't change. Now we can add 2,980 and 3.8 to end up with 2,983.8 times 10 to the power of 2. Now, one difference between these two is that when I chose the largest exponent, in the end, I ended up with a value that was already in scientific notation. However, here, I have a value that's not in scientific notation because the significand is larger than 10, well, larger than or equal to, I guess you can say. But so long as it's larger than 10, this is not scientific notation. Even 10 is not scientific notation. We need 1 non-zero digit on the left, which means now I have to move the decimal point back over 3 digits, and exponent goes up by 3. And we end up with the same value as we had before. Okay, now, if we go with any exponent that's lower than the largest exponent, then this will likely happen, and you will have to adjust the location of the decimal point. If you go with the largest exponent, then no guarantees that at the end you don't have to move the decimal point and adjust the exponent to write the result in scientific notation, but chances are lower. It depends also on how many numbers you're adding and subtracting, and even if it's off, at least for 2-3 numbers, let's say, it will be off by maybe 1 digit, maybe 2 digits, and that's not too difficult to handle. With other alternatives, it can be worse. Now, if you pick 5 as the common exponent, then all other exponents, or 5 in this case, the largest, then all other exponents will have to go up, decimal points move back. If you go with the lowest exponent, then all the other exponents have to go down, decimal point moves forward. That's how you end up with multiple digits on the left side. And if you go with something in between, if I had chosen, let's say, 3, then some of the decimal points would move forward, some of them would move backward, and that would become a little bit annoying to work with. So again, the recommendation stands. that you should go with the largest exponent of 10 that you see. Alright, problem number 5. Now here I have an example when we have a negative number and then we subtract another with an exponent of 10 that's negative. So negative 9.14 times 10 to the power of negative 2 minus 3.8 times 10 to the power of 1. And we go with the largest exponent, which is 1, and therefore we need to change this to times 10 to the power of 1. That means exponent goes up by 3, and therefore decimal point moves back over 3 digits. We have negative 0.00914 times 10 to the power of 1, and the second argument of the subtraction stays the same. Now because we have two losses in a row, we add them. There will be a total loss of 3.80914 and then times 10 to the power of 1. Alright, I believe this is the last problem. So now we have three numbers, and the exponent of 10 is different in each one. We have times 10 to the power of 3, times 10 to the power of 2, and times 10 to the power of negative 1. The largest exponent is 3, and therefore we convert all of the others to equivalent values that use times 10 to the power of 3. Now you notice again that I don't have to go through the logic that exponents go up. So which way does the decimal point go? Because all of the exponents go up, all the decimal points move back. 2 is 1 away from 3, so decimal point moves back over 1 digit. And we end up with 0.999 times 10 to the power of 3. Negative 1 has to go up by 4 to get to 3. Decimal point moves back over 4 digits. And we get minus 0.000682 times 10 to the power of 3. Now we do the addition subtraction chain 9.67 plus 0.999 minus 0.000682, and that gives us 10.668318 times 10 to the power of 3. You notice that even though this time I went with the largest exponent, my answer is still off. I need to have one non-zero digit on the left, but it's not so bad. It's only one place. Decimal point moves back, exponent goes up. 1.066818 times 10 to the power of 4. Now, one more thing to keep in mind, by the way, is that such an answer, as we discussed in an earlier video, would be rounded. Like, this is too many significant digits, of course. Perhaps to something like 1.07 times 10 to the power of 4. This one as well would be rounded to perhaps negative 3.809 times 10 to the power of 1. Okay, before we end the video, let me talk briefly about what happens when the exponents vary greatly in size. So for example, 5.97 times 10 to the power of 24 plus 9.109 times 10 to the power of negative 31. You can imagine how many digits I have to move the decimal point over when negative 31 goes up to 24. That's an increase of something like 55, 54 or something like that. And the decimal point has to move back over that many digits, over 50 digits. And you might wonder, how do we deal with situations like these? In practice, these situations do not happen. If they did, then we would ignore the smaller number. Let me give you an example of that. So if I put some context behind these numbers, 5.97 times 10 to the power of 24 is the mass of the Earth. It's that much. More than trillions and quadrillions and so on kilograms. Whereas the second number, 9.109 times 10 to the power of negative 31, is the mass of an electron. And you can see there is the decimal point. You can see how tiny this mass is. And doing the addition here would amount to trying to find the sum of the mass of the Earth and an electron. And I highly doubt that anyone would try to do that, because we would say probably that it's the same as the mass of the Earth. Like, the mass of an electron is so tiny, it just pales in comparison. It gets lost in the level of approximation that we have, because this is rounded, of course. And so how can you add a value that's so tiny to something that has such a large level of error? Because again, this is an approximation. So in such cases, in case they come up, we just say the answer is the same as the largest number, 5.97 times 10 to the power of 24. And that will be the same as saying if you add the mass of an electron to the mass of the Earth, in the end it would be pretty much the same as the mass of the Earth. Alright, so in practice, the difference between the exponents is not that large. Even here, with a difference of 4, you can see how many decimal digits were introduced in the smaller number. This is very tiny compared to that. Okay everyone, thank you very much for watching this video. One more video on scientific notation coming up, I'm hoping right after this one, on multiplication and division of numbers that are written in scientific notation. Take care, and I'll see you in the next video.